Now that we have an introduction as to when and why to use quantum mechanics, we want to move on and start applying quantum mechanics using the postulates we just looked at to specific systems. And we'll start out with very simple systems and move to more complicated and interesting systems as we move on through the course. We want to start out with the simplest system we can handle, and that is a free particle. A simple particle that has no forces acting on it and is only free to move in one dimension. So it's got constant potential energy. And so classic mechanics would say, Isaac Newton would say, force equals mass times acceleration, where acceleration is the second derivative of position with respect to time, and the total number of forces is zero if we're dealing with a particle we're describing in this way. And position is related to original position and velocity of the particle. This is one of the fundamental equations that you would go over in a first semester physics course like Physics 111 or Physics 221. X0, original position, and V0, original velocity, are constraints that come from integrating the original function here. The quantum mechanical version of this takes a look at the Schrodinger equation and says that energy times the wave function for the system is equal to the second derivative of the wave function with respect to x times these constants, negative h bar squared over 2m, and then all of that is added to the potential energy times the original function. If we assume the potential energy to be zero, just to make our math a little bit easier, then that term can drop out, and we can say that the wave function has to be a function such that the second derivative of that function with respect to position gives us the original function times negative 2 times the mass over h bar squared times the energy. So that's just an algebraic manipulation of Schrodinger's work. And so we need to think about what wave functions might be a solution to this equation. Now remember, when we solve a quantum mechanical equation, we're usually not solving it for a constant like E. We're solving it for a function to find out what function satisfies that equation. There are trigonometric functions and exponential functions that meet that criteria we just described for the second derivative. So for our purposes, to make our math a little bit easier in this case, we'll use the exponential function. If we take the second derivative of this particular exponential, we get exactly what was required on the previous slide. And that's also going to work if the exponent is negative I rather than I. So we take second derivative and we get the original exponential times the square of the coefficient of x up here, this term we have under the square root, times I, or negative I. Now what we can do to make our math a little bit easier is devise a constant that we called k, and we've used this constant before. K is 2 pi over lambda. But you can go through and try this on your own. If you wind up not being able to reach a point where you trust me or believe me on this, use de Broglie's equation that relates wavelength to momentum and h, and convert h to h bar with the proper 2 pi's, and you will be able to derive this expression that says that k, if k is 2 pi over lambda, 2 pi over lambda, which is k, is also the entire term that's under this square root. So they're equivalent based on the fact that 2 times m times kinetic energy is the square of momentum. So the square of momentum over the square of h bar, all square rooted, is momentum over h bar. And so like I said, you should be able to work that out. I can prove it for you in class if we need to. So that means we have these two wave functions where k is 2 pi over lambda. And these would then be plane waves, each moving in the opposite direction from one another, and each having their own eigenvalues based on the kinds of operators that we would use on them to predict observable quantities. This is similar to the classical result in that we find a particle with constant energy, constant velocity, that is dependent only on its initial velocity. The energy spectrum turns out to be continuous in this case. That won't be the case in any other quantum mechanical problem. We will have step or quantized or digitized energy values for any other quantum mechanical system. The difference here between this and classical mechanics is that in this case we can't calculate an actual position for the particle like we could using Newton's equations. We can only calculate a probability of finding it in a particular space or area. We also can't normalize this wave function, at least not over all space. What we can do though is normalize it over a particular length and then say, all right, L is very large or on the order of infinity. So the probability function, probability density function for this, we get by squaring the wave function and then dividing by the normalized wave function. And so if we go ahead and do that, notice that E times e to the negative ikx times e to the ikx, if we add these components, ikx minus ikx is 0, e to the 0 is 1, so we get a times a on the top. That will cancel with the a times a on the bottom, and so and then we integrate this from negative L to L. Since again we get 1 here, we're just integrating dx. And so we get that the probability of finding a particular particle in a particular area dx is dx, the area itself, over 2L. In other words, it's not any more probable to find the particle in one place along the axis than another. And we'll get the same result if we use the negative version of the wave function that we derived on the previous slide. So probability of finding the particle in a particular position is independent of where we look, which means nothing at all can be specified about the position of the particle. And the question comes up, why is that the case? And the hint that we can give you is that the momentum of the particle, depending on which wave function we work with, is going to be h bar k or negative h bar k. So the particle is equally as likely to be moving one direction along the x-axis as the other, and therefore it's equally as likely to be found in one spot as another. Now, if we want to work our way to a slightly more complicated and a bit more important and usable and practical of a system, we can confine the particle to a one-dimensional box. So instead of saying the particle has free reign over the entire x-axis, we say that the particle is stuck here between some point along the x-axis and another point. The way we can specify that is we say the potential energy of the particle when it's in here is 0, and the potential energy of the particle when it's outside is infinity. In other words, there's some infinitely large barrier that keeps the particle from going from here into this area. So it's like the free particle, except for that the potential energy is only 0 inside the box when x is between 0 and a, or in the picture we use 0 and L, and it's infinity when it's outside of the box. So again, we take a look at Schrodinger's equation. We've rearranged it the way we did previously to solve for second derivative. This time we'll leave the potential energy term in there since we have to talk about that a little bit. And realize that the second derivative would be infinite outside of the box because v would be infinite. And so E would never be large enough to be smaller than infinity when we subtract from V. And that means that we would violate the conditions of the first postulate. The only time that wouldn't be true is if the wave function is zero. So the first postulate's conditions force us to call the wave function zero to the left of the box and to the right of the box. So the wave function is going to be zero everywhere except inside of the box. So we'll call that a boundary condition. Not only does the wave function have to be zero outside of the box, but we have to choose a wave function for inside of the box such that the wave function will be going to zero and reach zero as it reaches the edge of the box. So the box has to end at each point at specific points along the wave function, at nodes, at places where the wave function is zero mathematically. So inside the box, the solutions, the wave functions, are the same as they would be for the free particle, but it's going to make our math a little bit easier in this case if we use the trigonometric equivalent. So we'll say the wave function is a times sine of kx plus b times cosine of kx. Now, the wave function has to be zero when x is zero because of our boundary condition. So if x is zero, the sine of zero is zero. This term would drop out. The sine of zero is 1. So that would mean if the wave function has to be zero, b has to be zero. So this term is gone from the wave function. Our wave function is now a times the sine of ka, where a is the normalization constant. And if we want that to be zero when, the wave function now is a times sine of kx. If we want that to be zero when x is a, when x is the other edge of the box, that is only going to be true when Ka is n times pi, where n is some integer. So now we can say that K has to be n pi over a in order for this function to satisfy our boundary conditions, and n is some number that's between some whole number between 1 and infinity. To find a, we can normalize the function. Since the function only exists between 0 and a, we'll integrate the square of the function over that space, and we get a value for that by using the standard integral. That integral of sine squared times a constant times y is y over 2, or in this case x over 2, times the sine of 2 times the original, minus the sine of 2 times what was originally inside the sine, all over 4b. So when we do that, we get this expression, and when we substitute that out between 0 and a and set that equal to 1, you guys can do the math on this on your own, or I can do it in class if you need me to. We'll realize that the wave function has a normalization constant of 2 over the square root of 2 over a. Alright, so there's our wave function for the particle in the box. And in our next video, we will push on and finish applying the Hamiltonian operator to this wave function and solve for the specific energy levels of the particle in the box.